Hello everyone, my name is Luke Bradshaw and I'm a senior in material science engineering at Tech. I wanted to talk to you today about ceramics, which is one of the categories of material that we work with. Ceramics are generally hard, brittle materials. They have general good heat resistance and corrosion resistance, and they're generally made up of mixed ionic and covalent bonding, but there's also a type called polar covalent bonding. What that means is that there's more charges on one side of the crystal lattice than the other, so if you change its shape, you can make a potential from one side to the other, which is a voltage, and you can use that to power lights or speakers or any other kind of thing. So we have one set up here. What's going on is we have our leads coming off of this guy, who's our little piece of piezoelectric film. So if I bend this, one side is undergoing compression and the other side is undergoing tension. And you can see on the voltmeter it jump up and down as I do that. And that can also be used to power lights. So I'll take you guys in the other room, we'll turn out the lights, and I'll show you that you can actually generate light with just movement using piezoelectrics. Yeah. So here are two piezoelectric circuits that I showed you out in the other room. Same setup and everything, but now I'm going to turn off the lights and you'll be able to see it light up. So just look at this LED here. It's a faint red glow. And then here's the other one, which generates much more voltage. So there's a lot of cool applications for piezoelectrics. Some of the most common ones are energy recovery methods of ways to take mechanical movement and turn that back into electrical energy. Some of the other more interesting ones is articulating movement on a very small scale. So if you want to move an object, let's say 2 or 3 atoms over, of a couple nanometers, you're not going to be able to do that using any sort of movement system that we normally use, like screws or pushing or measuring how far it's going. So what you actually do is you take a piezoelectric, and instead of squishing it to get a voltage, you run a voltage through it, which changes its shape. And that way you can dial in the voltage and get very exact fine movements, which they use for atomic force microscopes and other types of technology like that.
Hi, so I am Kendall. I am a junior at Virginia Tech studying material science and engineering. And these examples in front of you are some of the examples of ceramic materials in everyday life. So what we have here, this is a ceramic paint scraper right here. And you can see the end right here is made out of a very tough ceramic, so it makes it easy for the paint to be scraped off of, let's say, a wall or something like that, which you're trying to get rid of. The next example here is a ceramic foam. If you can see that right here, this is used for filtration, and so we have, let's say, molten metal is coming through. And what this ceramic foam does is it filters out different sort of particles that we want to get out. And so that basically we use, let's say, molten metal, pure molten metal right here. And so this third example right here, this is a catalytic converter. And what we see here, this is made out of a ceramic, and it filters out different gas particles via a redox reaction, a reduction oxidation reaction. And what happens is, let's say gas particles are coming through in, let's say, a car engine. And so the gas particles filter through and it processes this reaction. And what is left is it makes the gas less toxic. So these are just 3 examples of what ceramic is used for in your daily life.
Hello, my name is Thomas Canfield. I am a senior in materials science and engineering here at Virginia Tech. And so here I'm going to be doing a demo with a nickel and titanium alloy, which has been coined as a shape memory material. And as I will demonstrate, this is because when you look at this material, we're going to stretch this spring. And as we stretch this spring, it's currently in its martensite phase at a cooler temperature. But once we add heat, the phase is going to then change its crystal structure into the austenite form, which will then cause it to bend away. as you can see there. And then once again, in this material, it's the same principle of a phase change and change in the crystal structure given the heat. So we're going to coil this up and drop it into some hot water, and it'll straighten out this material. And as you can see, it's nice. Once again, this is a nickel titanium alloy. It's a shape memory material, and this technology is also commonly found in braces. So they use this to straighten out your teeth. So the increase in temperature in your mouth heats up the spring and causes your teeth to straighten out, as so.
Hey everyone, so another one of the really cool opportunities we have at Tech here is the opportunity to work with the foundry. We have a pretty large scale, medium scale metal processing and casting department. It's run by Dr. Drusich, and these are some of the things that were made. This is a hooky bird. That was actually a investment cast was made, and then it was cast out of, I believe, steel. And then it was painted, covered with an enamel to protect it. And then here are two more examples of cast pieces. What I wanted to talk about here is these two pieces are approximately the same age, but one of them was covered in a protective enamel and the other one was not. And you can clearly see that the one that was not covered is starting to corrode at a much faster rate than the one that was protected, which is why we use this sort of protective coatings on metals, is to keep them going. The last cool metal thing I have here, something we do a lot as materials engineers is we look at failure, how materials behave when they're put under different forces and how and why they fail. So one of the most classic examples we do is just tensile testing. So we take this bar and we machine it out so the middle is thinner than the outside pieces, which are where it's held. That ensures that it will fail somewhere in this thinner area. We then pull on it until it eventually snaps, and then we can look at the surface of how it broke and understand things about the microstructure of the metal and how it behaves under force. This is very useful, and this is not only done for metals, but we also do this for polymers and different composites, just trying to test them in different loading conditions and see when and why, more importantly, that they fail.
Hi everybody, I'm Tim Ruhr. I'm currently a senior in material science and engineering, and I'm going to show you a little bit about how superconductors work in magnetic fields. So, as you can see here, we have a magnet, which I'm holding in the tweezers, and a superconductor, which is here in the pan. And as you would expect, under current conditions, when you place the magnet on top of the superconductor, nothing happens. So now we're going to cool the superconducting material. We're going to do that with liquid nitrogen. We're just going to surround the material with this cold substance, and that's going to chill it. So as you can see here, we have the magnet actually hovering over the superconducting material itself. As you can see, the magnet is suspended in air. It bounces and it's not held up by anything except the interaction of the magnetic field of the magnet and the superconducting material itself.
Another cool effect with liquid nitrogen is something called the Lindenfrost effect. And liquid nitrogen is very cold because it contact with your skin for a long time. It can hurt you, but if you just pour it on top of your skin, it just rolls off immediately. So what's happening there is as soon as the liquid nitrogen contacts your skin, it vaporizes, turns into a gas, and that layer of nitrogen gas actually protects you and acts as an insulator between you and the super cold liquid nitrogen. That way it can just roll off your hand. The same effect can also be observed when you see people wet their hand and touch molten metals and they don't get burnt. It's that same thing. That layer of gas that forms immediately acts as an insulation barrier and actually protects you from the thermal effects of either cold or hot. So another cool demo of metals is the example of something called screaming tin. So tin, when it crystallizes or solidifies from a melted stage, it actually starts twinning. So what twinning is means that two crystals share the same lattice point and can grow over each other. So the result of that is that when you put dislocations through the material, it actually shears off those twinned crystal lattices, and you can hear the sound when you bend tin. It sounds like a crackling, kind of high-pitched popping sound. But I'll put it next to the phone and see if you can hear it. It's pretty cool stuff. So tin actually isn't the only metal that does this. Also gallium does this, indium does this, and I think one or two others. It's just a result of the crystal structure of this type of metal.
Hi, my name is Anna. I'm a senior here at Virginia Tech in Material Science and Engineering, and one of the things I'm going to be telling you about today are our design teams within this department and the conferences we get to go to. So every year we go to this really big conference in the fall. It's called MS&T, which stands for Material Science and Technology, and we bring 3 different design teams to compete. One of them is the dome team. So each year we design a different dome and we bring it and we compete against other schools, and essentially they place it under this really big hydraulic press and push down on it as hard as they can, and the team that handles the most pressure wins. So these 2 actually maxed out the machine and took as much force as possible, and this one actually broke the machine, so no other teams could really test anything after us. But this one is really, really fun. It's super energetic, and all the schools are competing against each other. And then we have 2 other teams that are ceramic and glass based. So one is called the ceramic disc team, and this is one disc that was entered in the aesthetic competition. So every year you can enter the aesthetic competition or the throwing competition, or both. So you have to make a disc that's made of a ceramic or a glass that fits into certain parameters that are set by the judges. And then everybody goes, and for the aesthetic competition you just lay them out and the judges judge them against each other. And then for the throwing competition, each team sends out one member to actually throw the ceramic disc into a disc golf net, and whoever's takes the longest to break, like you step back a distance every time you throw, and whoever throws it the longest without breaking wins the competition. So when I went, we actually won that one too. It's super awesome. There's like bleachers full of students, everybody is cheering, and it's really, really fun, and you actually get a cash prize too, so that's not bad. You get a cash prize with these ones too. And then the third competition is ceramic and glass as well. It's a mug drop competition. So essentially it's similar to the disc competition, but it's just dropping a mug from varying heights off a ladder. So again, bleachers full of students, everybody submits a mug to the competition, and the way that you win is that after each drop they test your mug to make sure it can still hold water, and if it does, then you get to move on to the next round, because a mug doesn't function if it can't hold any liquid. So whoever's can get dropped from the highest height without breaking and essentially not being able to hold water wins. That one's really fun, super high energy, and it's a really great opportunity not only to compete against all of these other schools, but also to network with them. I met a bunch of professors and students from schools like Clemson and Penn State, and just kind of networking in the material science community is a really, really awesome opportunity, even though we're competing against all of them.